Good afternoon, class. We are looking at section 4.6, Antiderivatives. So we've seen differentiation formulas, and we need to be very comfortable with them so we can move on to the reverse process, or antidifferentiation, or integration. Integral calculus, it has two parts. Differential calculus, which deals with instantaneous rate of change and slope of a tangent line, and integral calculus, which deals with accumulated change and area under a curve. Both parts rely heavily on the concept of a limit, and they are intimately related. One is the reverse process of the other. Integral is the opposite of a derivative, also called antiderivative. So the question is, given the derivative of a function, what is the original function? Can we find the original function? The antiderivative of f of x is the set of functions f of x plus c. It's a family of functions such that the derivative of capital F of x plus c is lowercase f of x. Generally speaking, lowercase f represents the derivative of uppercase f. And the constant is called the constant of integration. As you know, the derivative of every number is 0. So it doesn't matter what number you have there. When you want to come up with the antiderivative, it is not a unique solution, but a family of solutions. That's why it's called indefinite integral to begin with. Antidifferentiation is often called integration to indicate the antiderivative of x squared is x cubed over 3 plus c. We write it in this fashion. This is the integral sign. The integral of x squared dx is x cubed over 3 plus c. Or the integral of lowercase f of x dx is capital F of x plus c. Capital F of x plus c is a general form of an antiderivative of f of x. This is an elongated s. It's an s. So if you have two functions, capital F and g, that are any two antiderivatives of f, then capital F prime and capital G prime are the same, lowercase f of x. Then f and g have a relationship such that they differ by a constant. So one is the other one plus a constant. That's the idea. So let's look at some warm-up examples. We want to come up with the indefinite integral. First and foremost, the concept of dx will give us the independent variable, namely x. So we want a function. When we differentiate, it gives us 8, and that would be 8x plus a constant. And again, let's assume this was a t, then the answer would be 8t plus the constant. So this will tell us the independent variable is x. So this is dy. This is f prime of x dx. And we can check by differentiating the right side. It gives us the 8. Another example, we've already done that. We know the answer is x cubed. And all we have to do, differentiate the right side. And we get to 3x squared. This without the dx. Okay. Just for the sake of argument, the integral of e to the power of x dx. Which function do we differentiate to get to e to the power of x? Anybody? What function would be the answer here?
E to the x.
Beautiful. E to the power of x plus c. Simply because if you differentiate the right side, you get e to the power of x. How about the integral of 1 over x dx? Can you think of a function you differentiate, it gives you 1 over x?
Natural log.
Perfect. And the reason we use an absolute value, I've already explained that to you, because the domain is 0 to infinity. So all you have to differentiate the right side, and it gives you 1 over x, or x to the power of negative 1. So let's look at some basic integration formulas by looking at differentiation and then coming up with the integration. First of all, you have a constant, you know the derivative is 0. So let's go with this one. What is the derivative of kx, where k is a number, is a constant? The answer is k. Therefore, the integral of k dx must be kx plus a constant. And here's the power rule. And I want to discuss the power rule. When we differentiate, we multiply by the exponent, and the exponent goes down by 1. The integration is the reverse process. So instead of taking the exponent down by 1, we take it up by 1. So that makes it n plus 1. Instead of multiplication by n, we divide by n plus 1. So notice from here, we should be able to see why this is the case. And this is the reverse process. Remember, with the differentiation, we multiply by n and we take the exponent down. Now, in this case, you have to take the exponent to 1 up, so n plus 1, and then divide. Instead of multiplication, divide. Now, by the way, n can't be negative 1. We'll see in a moment what that means, of course. I want to show you by differentiating this side. So if I differentiate this, I want to differentiate this. So I get, so let me write it down, d dx of what is given is 1 over n plus 1, x to the power of n plus 1 plus a constant. That constant gives us 0. So we know the answer is 1 over n plus 1. Then we're going to multiply it by the exponent. And then the exponent, we subtract 1. As you can see, these two cancel each other, and we get x to the power of n. So in essence, we are proving that the integral of x to the power of n dx is x to the power of n plus 1 over n plus 1 by differentiating the right side. Let's continue. E to the power of x, the derivative is itself. So the integral of e to the power of x is e to the power of x plus a constant. Ln x, the derivative is 1 over x. So the integral of 1 over x, also x to the power of minus 1, is a natural log and a constant. The derivative of sine is cosine. So the integral of cosine becomes sine. The derivative of cosine is negative sine. So the integral of negative sine is positive cosine, or the integral of sine is negative cosine. So take a look at this patch in a matter of comparison. E to the power of x, 1 over x or x to the power of minus 1. If you go back to this power rule, we said n can't be negative 1 because when it is, it gives you a natural log. The derivative of sine is cosine, so the integral of cosine is sine, and the derivative of cosine is negative sine, so the integral of sine becomes minus cosine. Let's look at more trigonometric functions. The derivative of tan is secant squared. So the integral of secant squared is tan x plus c. The derivative of cotangent is minus cosecant squared. So the integral of positive cosecant squared is negative cotangent x plus a constant. The derivative of secant is secant tan. So the integral of secant tan is secant x plus a constant. The derivative of cosecant is negative cosecant cotangent. So the integral of cosecant cotangent becomes minus cosecant, and of course, all of them plus a constant. So I hope you see the relationship above. There are a couple more interesting formulas. One of them, a constant multiple. We did the same thing in the case of differentiation. If we have a function multiplied by a number, whether we differentiate or integrate, this multiplier remains. So you can put it in or outside the integral sign. Sum and difference rules. Same thing with the differentiation. When you want to differentiate, you do term by term. When you want to integrate, you do term by term. As you recall, the derivative of e to the power of kx is itself times k. So if I want to integrate that, the reverse process is the same thing divided by k. And all you have to do, differentiate the right side. You see, you get e to the power of kx. So these are basic integration formulas. With a little bit of a practice, we become good at it. Let's look at some examples. Here's the power rule. The integral of x to the power of n dx is 1 over n plus 1 x to the power of n plus 1 plus c. Therefore, we're going to use the power rule. We're going to divide 1 by 7 plus 1, and then x to the power of 7 plus 1 and a constant. So whether you want to write this intermediate step or not, that's the final answer. Very straightforward, everybody. What would be the answer here? Anyone? Well, we add 1 to 99 becomes 100. So 1 over 100, x to the power of 100, and a constant. We are using the power rule for both cases. What about here? The same rule as differentiation. When we want to use the power rule, first we have to use the algebra to change this to x to the power of 1/2. So this step, which is an algebraic step, is the same as what we did in the case of a differentiation. Now we follow this rule. We add 1 to 1/2. So 1 over 1/2 plus 1, x to the power of 1/2 plus 1, don't forget, a constant. 1/2 plus 1, 3/2. 1 over 3/2 flips it over to 2/3. Same thing here. If we were to differentiate, we would rewrite it as such. Then we would add 1 to -3, divide by it, and x to that power. So 1 over -3 plus 1, x to the power of -3 plus 1, and a constant. So this becomes 1 over -2. This becomes x to the power of -2. 1 over -2 or -1/2. And we put this one down, becomes -1 over 2x squared and a constant. We want to integrate e to the power of 4x dx, and e to the power of kx is itself divided by k. So 1 over k e to the power of kx plus c. So in this case, 1 over 4 e to the power of 4x plus c. Following the rule, 1 over k, that means 1 over 4. Following the rule, 1 over k is -3. So 1 over -3 or -1/3, and then the same thing. e to the power minus 3x, and a constant. Now, we do exactly the same here, but for any reason, if we can't see this properly, we change this to e to the power of 1/2 x. So x over 2 is 1/2 x. Therefore, your k is 1/2. So 1 over 1/2 or 2. Therefore, 2 e to the power of x over 2 plus a constant. So again, the reason I'm writing it in this fashion, because I want to make sure we see the exponent is half of x, which means k is 1/2. Again, if you see that, you don't have to rewrite it in that fashion. Now, reminding everyone that the integral of 1 over x dx is natural log and a constant. So in this case, again, if you notice it's a natural log, so be it. If not, let's rewrite 2 over x as 2 times 1 over x. Therefore, the 2 remains, and this has this answer. So the same thing times 2. 2 ln x, NL of absolute value of x plus a constant. What about here? Let's rewrite it again as 1/2 times 1 over x, because just to make sure everybody can see this, really, this part is using the natural log. So the same answer, put the 1/2 in front of it. So changing it to this format, it's really helpful to see what you're doing. Now, to integrate this, you have to do it piece by piece. So let's give everybody a moment to integrate this term by term. Go ahead and write it down, term by term. Now it should be pretty obvious what the answer is. The exponent is 4 here. You take it up, becomes 5. So 2 over 5 x to the power of 5. The exponent is 3. We take it up to 4. 3 over 4 x to the power of 4. 2, we take it up to 3 minus 7 thirds x cubed. Plus this one, I hope everybody can see it's x to the power of 1. So 1 over 2x squared minus 5x and a constant. 2 over 5x to the power of 5. 3 over 4x to the power of 4. Minus 7 thirds x cubed. X gives you 1/2 x squared. Minus 5x and a constant. Let's look at part B. We are going to square this using the fact that a minus b squared. Again, refreshing your memory. Is a squared minus 2ab plus b squared. This is x squared minus 10x plus 25. This gives you 1/3 x cubed. This one minus 10 over 2 or minus 5x squared. This one 25x and a constant. So very straightforward. Here's the next one we want to integrate. Now, the first step is to divide everything by x squared, just the way we would do with the differentiation. So we make up three fractions. We've seen this type of question in the case of differentiation. This gives you 1. This gives you minus 7 over x. This gives you 2 over x squared. And this is obviously x minus 7 times 1 over x minus 7 ln of x in an absolute value. I want to again remind you how we deal with this guy. First, we change it to 2x to the power of negative 2. Then we divide the 2 by negative 2 plus 1, x to the power of negative 2 plus 1. Negative 2 plus 1 is negative 1. So we have negative x to the power of negative 1. I forgot to put the 2. This is negative 2 x to the power of negative 1. The reason it's negative 2 because 2 divided by negative 1 is minus 2. And that will change to minus 2 over x. So 1 gives you x, minus 7 over x gives you minus 7 ln of absolute value of x, and 2 over x squared gives you minus 2 over x, and a constant. Well, let's remind everybody the integral of cosine is sine. The integral of sine is negative cosine. Since this is cosine, the integral is sine. However, pay attention to the fact that we are dealing with the variable t, not x. So 1 doesn't give you x, it gives you t. So t plus sine t and a constant. That's the thing you want to be careful of. If you don't use the proper variable, it will be wrong. We want to integrate this, and again, the first step is to change this. Now, before we move on and changing that, notice, of course, sine. The integral is minus cosine because it's negative sine. So this part becomes positive cosine. Let's concentrate on this by writing it as x to the power of 1/3. And now, if I want to integrate 1 over 1/3 plus 1, x to the power of 1/3 plus 1. 1/3 plus 1 is 4/3, so we have 1 over 4/3 x to the power of 4/3. Now, 1 over 4/3 means the reciprocal 3/4. And you can leave it like that, or you can write it in this fashion. I hope everybody can see this is the same as cube root of x to the power of 4. And as I explained here, minus sine x gives you plus cosine x. And of course, as always, we have a constant. Solve the initial value problem. dp dt is 2e to the power of 3t plus p of 0 equals 1. So first, let's remind everybody of the meaning of this. What is the definition of the initial value problem? Remember, when we solve an integral, it creates a constant. If there is a way to get rid of the constant, now we don't have a family of a function, we have a specific function. One of those is called initial value problem. So any equation containing a derivative is called a differential equation of d. We've been solving that. So for example, when we solve this, this is a differential equation in essence, but it creates a constant. A function which satisfies the equation is called a solution to the differential equation. So that is the solution. An initial value problem is a differential equation along with a specified value of the unknown function called the initial condition. So what happens is this causes us to get rid of the constant. So for now, I want you to ignore that and just deal with this. To solve this, first of all, dp is the product of these two, and you are integrating this, which means the integral of the left, integral of the right. dp becomes p of t, and let's integrate this one. Now, using that, 1 over k, remember k is 3, so 2 over 3 e to the power of 3t, and a constant. This is what we have been doing so far, nothing brand new. So if you ignore that, this is exactly what we have been doing so far. What is this? This is going to give us the following pair. The independent variable happen to be t, sometimes it's x. It gives us this pair 0, 1, which means if you replace the t with 0, and p of t with 1, we can find the c. So let's do that. So according to this, p of 0 is 1, so which means this pair. So replace, so p of 0 is 2/3 e to the power of 3 times 0 plus c, and that is equal to 1. So we are writing this. Needless to say, this is 1 because e to the power of 0 is 1. So 2/3 plus c is 1, and c is 1/3. And a family of functions, by replacing 1/3 becomes one unique function. So it's a general solution here. There are infinitely many different solutions with the constant. This is a unique or a particular solution. So the purpose of the pair is to find C, known as initial value problem. Let's look at another example. First and foremost, please understand this means we have the following pair 1, 5, or y of 1 equals 5. That's the meaning of it. That's the meaning. So for now, we're going to ignore that and just go with the integration dy dx or f prime of x. So let's multiply by dx. dy becomes that. And if I integrate both sides, that means integrate this side, integrate this side, this becomes y. And now let's integrate the right side. By now, we are pretty comfortable with that. First of all, this is a natural log, and we know that. Let's look at this one by changing it to x to the power of 1/2, and then bringing it up for the sake of using the power rule. So this one is natural log. What happens to this one is 1 over negative 1/2 n plus 1, x to the power of negative 1/2 plus 1, and a constant. So this gives you ln x, and this 1 over n negative 1/2 plus 1, x to the power of n negative 1/2 plus 1. Now what is negative 1/2 plus 1? Is positive 1/2. And this becomes 1/1/2 of 2. And this becomes 1/2. So we have 2 x to the power 1/2 or 2 squared of x. So the final answer is ln of absolute value of x plus 2 squared of x plus c if we ignore this. That would be what we have been doing all along. But now that we are going to use this, will give us the constant. So let's plug in 1 for x becomes ln 1 plus 2 squared of 1 plus c, and 5 instead of y. So y becomes 5, and we plug in. ln 1 is 0, square root of 1 is 1, 2 plus c is 5, and c becomes 3. Replace it, and that's your final answer now, which means this is the general solution, and this is a particular solution. In other words, first we have a family of functions, infinitely many different functions. Then, with the help of one pair, we find the constant and we have one solution. Let's look at one more example of that. We want to find the capital F. If capital F prime is this and f of 2 is 1, and again, I want to make sure we know that this refers to the pair 2, 1. So let's integrate this. Very straightforward. This one gives you, so we are integrating this. This one gives you x cubed 3/2 x squared plus 7x and a constant. General solution. Let me write it. Why is it? Because it has a constant. We're going to use this pair, which means wherever you see x, replace it with a 2, and f of x or y, replace it with 1. Let's do the work. Eight. 4 divided by 2, 2 times 3 is 6, plus 14 becomes 28. So 28 and c, they add up to 1. C must be negative 27. And we are going to replace the c with that, and now becomes a particular solution. So from a general solution, with one pair, we find one solution, a particular solution. That's all it does. That's the meaning of initial value problem. I give you a pair, you give me the constant. That's really the bottom line. We want to integrate this. We've seen the differentiation of that, and the process is number 1, change this to x to the power 1/2. number 2, divide this one by this one by this one, make up 2 fractions. As you can see, again, this is elementary algebra. This is x to the power of 1/2. This is x to the power of negative 1/2. All of these elementary algebra steps get us ready to use the power rule. Elementary algebra. Let's look at the first one. 1 over 1/2 plus 1, x to the power of 1/2 plus 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1. As always, we add a constant. Done. Again, the only calculus step. This is the only calculus step, everybody, and we are done. We just have to rewrite it. Everything else has been algebraic steps, and from here on, the same thing. 1/2 and 1, 3/2, negative 1/2 and 1/2. When we divide by 3/2, we get 2/3. So let's just write it. When we divide by 3/2, we get 2/3. And we divide by 1/2, we get 2. And we are done. You can write 2/3 x to the power of 3/2 here, or in the numerator, makes no difference. Same thing. Last question. Could somebody read this, please? Okay. Anyone feels like reading for us, class? Wow. A sample of cesium-137 with an initial mass of 79 milligrams decays T years later at a rate of negative 1.82949 e to the power of negative 0.0231 T milligrams per year. Find the mass of the sample after 23 years and round your answer to 1 decimal. It's important to understand what's given. First, since we want the mass, we are going to let m of t represent the mass that we are interested in. And so if we are interested in finding m of t, what is this? The rate. This is dm dt, since we called it m of t. So dm dt, the rate of decay, has this formula, has these units, an initial mass. That means m of t equals 0. M of 0 equals 79, the same units, milligrams. So we should be able to find m of t first, and then m of 23. So again, we call the function m of t. So this one is dm dt. Initial mass m of 0, 79. We go through this process and we are going to find m of t, and then we plug in 23 to find m of 23. This is the process. And to find m of t, we have to integrate this. We're going to multiply by dt, this one. So we are going to integrate. So let me write this at top of it. So this means dm is negative 1.8249 e to the power of minus 0.023 t dt. And we are going to integrate both sides. So if I integrate this side and I integrate this side, the left side becomes m of t. This is a simple integration because it's an exponential function. This is a number, so it doesn't matter it's inside or outside the integral sign. So you're integrating this one, and never mind the number looks nasty. It's e to the power of kx. So you have to divide by the coefficient of t. So you have to divide by this number. So this number divided by negative 0.0231, and then e to the power of the same plus a constant. Again, we are dividing this by the coefficient of t in the exponent. This ratio ends up being positive 79. So m of t is 79 e to the power of minus 0.0231 t plus c, and there are infinitely many solutions here. What are we going to use? One pair 0, 79. 0, 79. So m of 0 is 79. So if I replace the t with 0, so if I replace the t with 0, I get m of 0 is 79 times e to the power of 0, which is 1, plus the constant, it's 79, so the constant must be 0. And so the formula m of t is the same thing without the constant. The constant becomes 0. So we found m of t. What we are interested after 23 years, m of 23. So replace the t with 23. And you have to plug it into a calculator to do the math. And then 1 decimal. So 46.4 milligrams. You want to pay attention to the fact that after 4 is 3, so it doesn't go up. I put a bunch of decimals so we can easily make a proper decision. And the final answer is 46.4 milligrams.